Welcome to the IEEE PELS educational videos. The title of this presentation is High Frequency Effects in Transformer Windings, and I would like to begin by thanking Sandun Karupu and Jorge Vega who invited me to put this presentation together. So without any further ado, let's begin. So effectively we've taken the solid conductor and divided it into a number of strands. And we pick each strand so that it's obviously less than the skin depth of at that particular frequency. In fact, I've taken a result from my good friend Charlie Sullivan, who's done a lot of work on Litz wire in transformer windings, and he essentially recommends using strands that are roughly a quarter of a skin depth. That's quite severe. Sometimes maybe we could use half a skin depth. But here's the limitation. If you take this rule here, quarter of a skin depth, then at 400 kilohertz or for a 50 AWG or 0.025 millimeter wire, that's the limit. Mechanically, you can't have a wire any thinner than that. And the skin depth for that wire at 400 corresponds to 400 kilohertz. In other words, if we go above 400 kilohertz, we're going to run into problems even with the strands in this conductor. We might push that out. I think we could probably go to maybe 600 or 700 kilohertz and still have a valid design. But the reason we have a limitation now is because if we go to 400 kilohertz or above, essentially we're going to come back to the skin effect in each of these individual conductors. And we also have a skin effect now at the bundle, because remember, all of these strands are connected at the end. So this bundle acts like a solid conductor in terms of its skin effect, where the current will be bunched to the outside strands. Also, we have a very complicated picture now with the proximity effect. We have the proximity effect inside the bundle. We have the proximity effect due to external magnetic fields. And then we have an additional proximity effect here where we would have the magnetic field outside the winding. So we have individual strands proximity effect, we have proximity effects across the bundle, and then we have the proximity effect due to the outside magnetic or external magnetic field. This makes the situation extremely complicated, and effectively there is no simple analytical solution to any of these cases. But we do have this limitation here. And by the way, all of these strands have to be individually insulated from each other. That means that in terms of the utilization of the window, then there's less copper in the window because there's more space for the insulation. And usually, if we are taking all things into consideration, for the same temperature rise, we're looking at a window that might be 30% larger. So that means a bigger transformer. It might be a small price to pay as long as the losses are bearable. Now, we did a very interesting experiment here. What we did was we wound a transformer with 15 turns in the primary and 15 turns in the secondary. And we shorted the secondary and we calculated the AC losses. Now, we started with a transformer with a solid conductor, and it was 1.3 millimeters in diameter. We then divided it into a number of strands, and we had We had 16 strands, we had 40 strands, and finally we had 160 strands. Now, I want to recall that all of the conductors here have exactly the same cross section. So let's take a look at this. If we start with the solid conductor, clearly we can see Dow's formula coming into play here. I should mention that we measured these AC resistance with an extremely accurate meter, so we could depend on the results. So here we are then with our skin effect, and as you can see, even at 200 to 300 kilohertz, we're already at an AC resistance 10 times bigger than our DC resistance. Totally unacceptable. But now let's go to the other extreme. Here we have our 160 strand Litz wire, which each strand is actually 0.1 of a millimeter. And you can see down even at 100 kilohertz, we've several factors less AC resistance than our solid conductor. But as we go up in frequency, when we get to about 600-700 kilohertz here, can you see that the 160 strand 0.1 millimeter Litz wire is actually now has an AC resistance greater than our skin effect in our solid conductor. And the reason for that goes back to our previous slide where we have our proximity effect between the strands, proximity effect between the bundles, and the proximity effect due to the external magnetic field, which actually wouldn't arise in this case because there is no external magnetic field. But nevertheless, we see the issue here. So I think this slide is quite useful in that it points out that there's a limitation to how much Litz wire we can use. And in actual fact, if we go to a high enough frequency, it'll become redundant. By the way, we would never operate up here because, as you can see already on this line, our AC resistance is 20 times bigger than our DC resistance. Okay, all is not lost. We can help ourselves by redesigning the winding. Now, I want to show you here, this is the winding we showed in our previous example where we had 2 primary turns and 3 secondary turns. And here's the finite element analysis picture where, if you recall, we had our highest current density at the intersection between the primary and the secondary, and that's why the red current density is shown here as the highest value. Now, what we're going to do instead of that is we're going to take 1 primary turn, we're going to insert our 3 secondary turns, and then our second primary turn. Now, because if we go back to Ampere's law, we've only 1 unit of current enclosing the primary here, so we'll have 1 unit of magnetic field. Then our 3 secondaries in the opposite direction will reduce that by 3 steps, and then finally we'll go back to 0 with our second primary turn. And if you look at the current density over here, it's quite easy. We can just, in terms of our magnetic field, we'll take the peak of each value and square them and add them up, and they come to 14.4. If we do the same over here, because our magnetic field now is only half of what it was over here, we actually end up with 4.4. Now, this is very crude, but as an approximation, we can see that we've reduced our proximity effect by roughly a factor of 3 by interleaving the winding. And you can see the picture here, there's no red part. And I just want to make mention, these were drawn to exactly the same scale. So you can see there's a much more even distribution of current density in the interleaved winding. So that's a help. Now, unfortunately, when it comes to winding transformers, it's not always that easy to put primaries and secondaries and interleave them. But if you think about planar magnetics, which of course is gaining a huge foothold now, we can do PCB layered windings where we can have a PCB for our primary, then we can have some secondary turns and another PCB. So that's quite possible. Now, the last sort of losses I want to deal with are fringing effects. And this arises now in modern power supplies where you have, say, your resonant converter, an LLC resonant converter, where you've 2 inductors and 1 capacitor, and you have a resonance between the inductance and the capacitance. And in order to create one of the L's, we usually have a gap in the transformer. And here I'm showing the gap in the center leg. Now, if I look at it at low frequencies, the fringing effect, the flux density will fringe around the gap and it'll impact on the winding here. Now you can see when I've blown it up here, the winding doesn't have a great effect on the distribution of the fringing field or external magnetic field to the gap. This is exactly the same as the issue we had with the skin depth at low frequencies in our single conductor. No, but if we go to 100 kilohertz, what will happen is we'll have eddy currents flowing in these conductors here to block out the magnetic field. This is just like a Faraday shield, and these eddy currents will create losses. Now, our experience has been that, you know, once you get up, a lot of these resonant converters now are operating in the megahertz range, and when you get up to the megahertz range, you'll find that these losses can be quite significant. Now, again, we don't have an analytical tool to calculate these losses, but the finite element analysis tools have become very powerful and much easier to use, and it's quite doable to calculate the losses for a case like this. We did try a little experiment where we ran the program for the finite element analysis with the windings at different distances away from the gap, and the results are shown over here for different frequencies. And essentially, while it's only just a rule of thumb, but essentially what conclusion we came to is that the winding should be at least 2 gap lengths back from the gap, so that we're effectively operating in this part of the curve where the AC resistance is greatly reduced compared to when the winding is very close to the gap and we have maximum fringing interaction. So that's just a rule of thumb. Another possibility here is to build a winding so that there's a V section here where there's no winding actually near the gap. So we just take out this part of the winding here. Again, now the planar magnetics with PCB layouts and so on make this very easy to achieve. So that's a possibility. Okay, well, that's the end of the presentation. I hope you enjoyed it. If you have any questions, I'm more than happy to take questions via email. My email address is wghurley@ieee.org. And if you would like to interact or ask any questions, I'm more